So day 32, daily LeetCode, bit of a different backdrop, but shorter time on the clock today. I'm just gonna do 30 minutes. I'm in a different location because I'm doing a small vacation, but the grind is non-stop. 30 minutes will be recorded, but I'll probably do like an hour today. But that is the play. Last time we did O1 matrix. That's what we're gonna do again. I'm still stuck on O1 matrix. I don't understand, so I'm gonna try part 2 and then see where we get. So O1 matrix once again, 3 days in a row. Or actually, I might actually O1 matrix or review. I think I'm gonna do review actually. So we're gonna do some review actually. So we actually have review. I'm gonna do some review instead, and then we're gonna do 30 minutes of review. So I think pretty much 2 days on O1 matrix now, so we gotta make some progress in other areas. So it is what it is. 30 minutes. So we have convert sorted array to a binary search tree. All right, so we're back. 30 minutes. We have convert sorted array to binary search tree. So we have an array, given an integer array nums, where elements are sorted in ascending order, converted to a height balanced binary search tree. A height balanced binary search tree is a binary tree in which the depth of the two subtrees of every node never differs by more than 1. So one way we could do this, I'm thinking, so we have sorted array, we're getting passed in an array of numbers, we're returning a binary tree. And so it's actually, since we have a array, we want to turn this to a binary search tree. So binary search tree is a tree in which every node, the left subtree of the current node is less than the entire left tree, the entire left subtree of the node is less than the node itself, and the right subtree is greater than the node itself. You can see that that's true for each node, but they specifically want it to be height balanced. So this would be when the depth of each subtree that does not differ by more than 1. In this case, we're fine, but we can see that there's not a unique answer depending on how you cut up the tree. And the nums are already sorted in increasing order. So since the array is already sorted, we'll always have at least one element in the array, and the numbers range from 10 to the 4 to 4. So since the numbers will always already be in the array, one way we could go about this, since numbers are already sorted, there's one way that we can actually, I'm thinking that it's also possible, I'm thinking that there's something with the BST, right? The numbers are already sorted in ascending order. If we do an in-order traversal on a sorted array, then that would give us the BST that we're looking for. So we're basically converting an array to a binary tree. It's just it's already sorted. It just has to be height balanced. So I think the height balance would just mean that we always choose the center node as our pivot. And so basically, if all the nodes are going to be left and right, that's going to kind of pretty much say that there's going to be like a binary search style sorting of like binary search style traversal through the array, right? Because we want 0 to be, in all these cases, right, these two cases, 0 is our center element. So for 0 to be our center element, right, we'd have to calculate the center of this array. And then from here, what element would go in between, right, the two elements here, we'd have to calculate the center for that. So I think there's a way we could do this, and that way, what we could do is we could do a recursive function that kind of is like a recursive binary search over the values. So just to get started on that, we could do helper do left. So I'm thinking the way we could do it is that if we have, let's say, a recursive function, this recursive function would actually not be iterating over the binary tree, right? It'd be iterating over this potential group of arrays. That being said, if we do it that way, right, we would have something like this. So 10, -3, 0, 5, and 9. So if that's the case, right, we calculate the center using the same method we do for regular binary search. We get 0, right? And since we're getting 0, right, that's going to be our node. We would create that node, right? And then maybe we could set the left, and we could call that function again, right? And it would set the node for that value, and then it would be set to the range as well. But we only want to include ranges that are actually possible, and we actually, our output wants, so our output does have some elements where we could actually not have children for every single node. So that being the case, we can create this helper function. And I think we can just return it with our range passing in the numbers, and it's going to return a node at the end, which should have everything we need, because at the end of the depth first search, the first call will be the head of the BST. So we should have start from 0 with a nums length -1. We'll pass in nums. So here we'll do helper left number right number nums, right? And we could return a tree node or null. Right, so we're basically turning a binary search into a recursive function. And so in this case, if this was a recursive function for a node, we would usually do if node, but we only want to work with this if left, right, is within the range, right? So if left is less than or equal to right, then we know we're in business, right? Otherwise, we want to return null, right? So in the case where we send 0 up to 5, right, we know that 0 is less than 5, so we're in business, right? So we want to create a node, right? And the node, right, is going to get a particular value. The value it's going to get is going to be dependent on pivot, right? So the left plus math dot floor right minus left, right, over 2 semicolon. Right, so now we're going to have our pivot. Let's say we pass in 0 and 5. We'd have 5 minus 0 is 5. Over 2 is 2.5. Floor is 2. So we have in our array to start, we have 0, 0, 1, 2, which would be 2. So 2 would be our starting point. So we'll create this tree node, right? Using its constructor, we're going to pass in nums sub pivot. Now we would have 0, right? We want to get those left and right subtrees, right? So it's a node dot left, right, equals, we forgot new here, we're going to call a helper, right, but with a new range that's going to be sans our pivot. So our new range is still going to go from 0, no, we'll go from left, right, to our pivot -1, because we already processed our pivot, right? And then node dot right, we go from pivot +1, very similar to a binary search, to right. Then we could return node. So just to run it in our heads, we call this with 0 going to the last element in the array, which would be last index in the array, which would be 4. So 0 through 4, 0, 1, 2, 3, wait, 1, 2, 3, 4, 5. So 0 to 4, right? 0 is less than 4. 4 minus 2 is 2, over 2 is 1, plus left, which is 0. Wait a second. 0 nums dot length. We definitely want our center to be 0. So maybe we actually do pass in, we pass in nums.length, maybe 1, 2, 3, 4, 5, right? We do -1, so we go 4. We'd say 4 minus 0 is 4 over 2. 4 minus 0 is 4 over 2 is 2. And that's fine because we have, right, 0, 1, 2 as our center element. We do tree node nums pivot, we get 0, and then we go into push a call of helper onto the call stack, right, with a new range of left, which is 0, to pivot -1, which is 1. Start between 0 and 1, right? Is 0 less than 1? 0 is less than 1, right? So we do, no, that's the index. We have negative, the index 0 is less than 1, right? And so we do 1 minus 0, 0 over 2 is 0.5, floor is 0. Right, so now we're going to choose -10, so the one we're going to produce is actually this one. We create a new tree node with that value, which would be -10, then we'd call left and right for that range. So in this first call, in this next call, right, we're going to push a third call of helper onto the call stack. We have node.left equals helper left, which is 0, going to pivot, right, -1, which would be -1. So if we go here, is 0 less than or equal to -1? It's not, so we return null for this -10 nodes left subtree, this left node. So we pop that off the call stack, go back up to that call for -10 and do it for right. So we'd go to pivot +1, right? Pivot at the time was 0, pivot +1, which would be left, right, would be 1, right? Because 0 plus 1 is 1, right? And right was 1. I'm going to say is left is 1 equal to, is 1 less than or equal to 1? It is. So right minus left, which is 0 over 2 is 0, floor is 0, plus left is 1. Create a new node with -3's value, right? Do left and right for both. That's going to give us null. We return the node, right, and it gets set to the tree. So we're actually building the tree recursively. We pop this call off the stack, we pop this call off the stack, we return the node. Now we're back to our original call of 0. So this entire subtree was created from node.left. We do the same thing with the node.right. Forgot to pass in nums. So that makes sense. I'm thinking our time complexity is going to be linear time, where n is the number of nodes in the tree because we have to visit all of them. It's going to be linear space as well because each recursive call is going to add a is going to choose the size of the call stack. So that looks good. I just want to read something to make sense. How to traverse the tree DFS. Pre-order, in-order, post-order, DFS. This strategy, adopt the depth first as the two general strategies to traverse the tree depth first. In this strategy, we adopt the depth as the priority, so that one would start from a root, reach all the way down to a certain leaf, then come back to reach another branch. DFS strategy can be further distinguished as pre-order, in-order, and post-order, depending on the relative order among the root node, left node, and right node. First search, we scan through the tree level by level, following the order of height from top to bottom. The nodes on the higher level will be visited before the nodes lower levels. So pre-order be 1, 2, 3, 4, 5. In-order is 1, 2, 3, 4, 5. Posters 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. In-order traversal of a BST. In-order traversal of a binary search tree is an array sorted in ascending order. So if we already have the array in sorting order, we just have to do a in-order traversal. So the array as an input, we could rewrite the problem as construct binary search tree from in-order traversal. let's go down what the problem is called. Does this problem have a unique solution? Can order traverse uses a unique identifier in code decode BST? The answer is no. In-order traverse is not a unique identifier of BST. At the same time, both pre-order and post-order traverses are unique identifiers of BST. These traverses, one could restore the in-order one. Both unique identifiers of whatever binary tree. So the problem sorted array to BST has multiple solutions depending on the center node you choose. Here we have an additional condition. Tree should be height balanced. Depths of the two subtrees of every node never differ by more than 1. Does it make the solution to be unique? No. Basically, the height balance restriction means that each step one has to pick up the number in the middle as a root. That works fine with arrays containing odd numbers of elements, but there's no predefined choice for arrays with even numbers of elements. That's true. One could choose left middle or right middle, and both choices will lead to different height balance BSTs. Let's see that in practice. So I think that same thing is governed by seal or floor basically here. So if we do floor, if we do seal, then we should get the other version in which -3 is actually below, on the right side of 10. So 0, 3, 9, 9, -10. And if we do floor, it should swap. Right, so that makes sense. So we'll reset it. So we have a number of islands. So we have a grid, which is actually a matrix of strings which returns a number. Given an m by n 2D binary grid, which represents a map of ones, land, and zeros, water, return the number of islands. An island is surrounded by water. It's formed by connecting adjacent lands horizontally and vertically. Making all 4 edges of the grid are surrounded by water. So we have to return the number of islands. 1 is land and 0 is water. So here we have a grid with all these ones. To return the number of islands, the output is 1, so we have 1 total island basically. We have 1 total island because all the ones are connected adjacently and horizontally. Here we have 3, right? But we only have a group of ones here that work adjacently and horizontally. And it's not connected to this one because they're all connected diagonally, but that actually doesn't count as a connection. And then we have 1, 1. So we have m equals grid length, n equals grid I dot length. These are the rows and the columns. If we do this with a depth first search, the columns being differing sizes actually wouldn't break the problem too much. And we know that we always have a matrix of at least 1 row with 1 column. Grids of I sub j is either 0 or 1. So one way to do this, right, we know that each group of ones is counted as an island. So what we could do is we could iterate through the matrix, right, and then from there, right, if we have a 1, we want to see how big the island is, right? So if we could, when we reach a 1, start a depth first search, which would clear the nearby islands, right? So if we could start at 1, clear up this whole thing, right, to 0, right? On our next iteration, because we'd be iterating through the entire matrix, we wouldn't be able to find another 1, which would give us a 1 island, right? Because there wouldn't be another 1 to find. In this case, if we start at 1, start a depth first search, we could clear out this 4 block here, continue iterating through, and there are 1s here, but after the clear, they wouldn't, right? We'd always go back down to here until we find 1 here, start a depth first search, try and clear nearby islands, but there's nothing to clear. Horizontally and vertically, that is. So we go right, 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 find another 1, increment islands, so we have 3 islands you can return. So implementation of that looks like let island equals 0, and we can do 4, let row. We just want to iterate over the entire matrix. So let's just say iterate over entire matrix. If we find a 1, start the DFS, right? And then we have to implement DFS up here. So to do that, we can say let row equals 0, while row is less than the entire grid's length, right? And then we'll do row plus, and then we'll have 4, let call equals 0, call is less than the grid, so row dot length, call plus. Then from here, all right, we're going to return, we got to make sure we return the island, of course. Now we said if we found a 1, right, at grid sub row sub column, right, and it's like they said, 0 or 1 is either a string of 0 or a string of 1. If we find one that equals a string, from there we would like to start a depth first search, right? But first, if we find if we find a 1, we would like to start depth first search. If we find a 1, we know for certain we have at least one island, and we'll do a depth first search, which clears the nearby islands. We haven't written this function yet, but what we'll need is at least a reference to the grid, right? Current row and column, right? So here we can implement the DFS to the grid, which is a matrix of strings, right? R, which is a row, C, which is a number, right? And it's not going to return anything, right? So how do we clear these nearby grids, right? So now we found a 1, we want to do a depth first search, right? We want to go up, down, left, right, right? And if we find one that's up, down, left, right, we want to do another call, right, which also goes up, down, left, right. And so pretty much we're going to go pretty much as deep as we can, basically upwise first. So we go up, right, can't go up, go right, right. Found one, try to go up, we can't go up, go right, right. Try to go up, we can't go right. Try to go up, we can't. Try to go right, we can't. We go down, right. Try to go up, right. And this is where we have to have at least some way, right? So when we're going back up to this 1 right here, we're gonna need a way to say that it's visited, right? In this case, it looks like this matrix doesn't really have some kind of like reflexive nature, where if we zero out this 1, that it would affect future solutions. It only actually helps us to use this as our way that we visit. That being said, we know for certain we're gonna have to at least mark something as visited, right? So we don't go back up, can't go right because it's 0, right? We know we don't want to visit zeros. Don't visit other zeros, right? We kind of go down, don't want to go. Try to go down, also 0, right? So we pop this one off, go back up here, right? We don't want to go left, right? Because left is what got us here. So we don't want to visit, we've already visited. We pop this one off, right? Can't go down because it's 0. We already visit this one, pop it off, right? Go down, right? Try to go up, we already went up. Can't go right, can't go 0. Go down, right? Try to go up, we already went to up. Go right to 0, down to 0, left, right? At this one we go up, right? We can go up, so at this 1 we go up. We already visit this one. Go right, we already visit this one. Go down, we already visit this one. And we go left, so we also don't want to visit. Ignore out of bound calls. So basically, if we want to do those things, right? Basically, if we're given a row and a column, when would we pretty much not do anything, just return? That would be when actually do, right? So we want to mark something as visited, right? We want to make sure this is an actual node that we care about first. To do that, basically, we want to know for certain, like, is this grid right? And we're going to use the safe navigation operator, right? Because it's possible that this is out of bounds, right? If this grid sub row equals a 1, right, then we're in business, right? And this line right here would check, right? If it's been visited, right, it wouldn't be 1. We don't visit other zeros, right? So it has to be a 1. And the safe navigation helps with ignoring the out of bound calls. So if it equals 1, right, then we're in business. And we could also do, just to make it simpler, we could also do if it equals 0, not because we check out of bounds, we don't want to visit other zeros. I actually think it's better like this. If it equals 1, then we know we're in business, right? So if we know if it equals 1, right, we definitely want to mark it as visited. So R sub C, right, is going to equal 0. We don't want to come back here. Right, but we also want to do these 4 calls, so we're going to go up, down, left, right. We have to have 4 calls, right? Those, all 4 calls are going to also need actually, I wonder if we only go if it equals 1, then technically we could just call depth first search 4 times, right? Because it has to equal a 1 to enter anyway, right? So if we do it this way, we can do grid, right? We want to go, like we said, up, down, left, right, or up, right, down, left, DFS, right? To go up, right, that actually be row -1, right? Column stays the same. Write this 3 more times, right? To go right, column, actually, it's, yeah, to go right, column, I mean, row would stay the same, column would increase. To go left, I mean, to go down, we actually add 1 to row, right? And to go left, row would stay where it is, but column would get subtracted 1. So if we look at this, I think this makes sense, right? We'd iterate through, right? Row is less than grid, row plus call is less than grid sub row, call plus grid sub row, so call equals 1. Start that first search, item plus equals 1, DFS grid, right? If the grid, which actually does equals 1, set it to 0, and then we're gonna go now try and go up. Well, we go up, right? And we try to do grid R sub R, right, -1, which actually is -1. It actually doesn't exist in the array, so we end up getting null, right? And null does not equal 1, so we don't even worry about it. And then we try to go right. Right, so we're still in 1, right? That call would return. Now we would try to go right, but we can go right. So I think this should work. Nice. So this is actually a shortened version of the other version I wrote. So this is actually pretty cool. I like this solution. So yeah, we're treating the map basically as an undirected graph where there's an edge between 2 horizontally or vertically adjacent nodes, values of 1. So we scan the map, the node contains 1, then there's a node that triggers depth first search during DFS. Every visited node should be set at 0 to mark as visited node, count the number of root nodes that trigger DFS. This number will be the number of islands, each DFS starting at some root where it identifies an island. So I think our version is much actually simpler than their versions. You don't need an if for each one. You might though, depending on if you can do a safe navigation or not. And then we have time complexity of m by n, right? Because we're going to visit every node in the matrix, right? And space complexity is O of m by n in case that grid map is filled with lands. Depth first search goes m by n deep. So it looks like you can do this with a breadth first search. So linearly scan the 2D grid map if a node contains a 1. So I'll actually say that for different versions. So that looks good. So we'll do another. We have trapping rainwater. So we have function trap, we have height, which is an array of elevations, right? Given n non-negative integers, right? We have n non-negative integers representing an elevation map where the width of each bar is 1, compute how much water it can trap after raining. So we're given positive only integers, height, right? Representing an elevation map, width of each bar is 1, compute how much water it can trap after raining. So we have 0, 1, 0, 2, so we can see that the numbers in the array actually map to these blocks, right? And they want us to calculate how much water it can trap. The output seems to be 6. 1, 2, so the blue blocks, 1, 2, 3, 4, 5, 6. The above elevation map, black section is represented by an array. In this case, 6 units of rainwater, blue section are being trapped. Right. I see n equals height length, which is the number of numbers in the array, and n always has at least one element in it. Interesting. If there's one element, then you can't trap water, right? Because we can see that here. If it's not surrounded by 2 cubes, you can't trap water. So height sub I can be 0 to 10 to the 5. So what I'm seeing from this problem is that basically need a way to check how much water we can trap. We can only trap water between 2 elements of at least equivalent or greater height, right? And that's just how the world works as well, right? If you have like, let's say if you had Lego blocks, if you had one this high and one this high, you could trap only as much water as the lowest height one. So that I think is what we're kind of seeing here, right? So I think what this means, right, is that if we find something with the lowest height, we just have to see if we can find another block, a Lego block, of same or greater height. Now if we do that, we can just iterate over the center, right, and subtract the minimum of the 2 heights from the current elevation to get how much water it stores. That being said, if we have an elevation of 1, right, the next elevation that we can use as of the same or similar height is 2. And so for 2, we would actually, the minimum of these 2 would be 1, right? That being the case, we would start from here, right? We would do 1, right, minus 1, we'd have 0 water, right? We'd go here, we'd do 1 minus 0, we'd have 1 block of water. Then we'd go here, right? We have 1 minus 2, we get negative 1, so we know we want to ignore, we can't have negative water. So we want to keep only positive waters. But this makes sense when we're going from low to high, but if you're high, you have to find the lowest pretty much height that can hold you. That seems like or the maximum lowest height that can hold you. So if we start from the right, we can find the highest index, right, that we can hold. And that's cool, but the problem is you have to kind of visit your whole left-hand side to know what that answer is. So for example, if we do map this 1 to 2, right, what if there's another highest block right here, right, and so the highest that would actually be is 3. So I think it's easier, we have a more definitive answer. We're going from low to high allows us to only have to look at, pretty much we almost instantly know as soon as we look at an elevation if it's the best we can do, whereas if you go from high to low, you never really know. You have to visit your entire array. So to leverage that, maybe we could use a 2-pointer version, where if we iterate from both sides of the elevation map, we'll only ever iterate from the side that's smaller, with the side which has the lowest elevation. That way we know that at the end of the day, the best we can do is keep going forward to find one of similar elevations where we're currently at. So to do that, we would have a left, which would start at 0, right, and a right, which would start at height length minus 1, right? And we could say while left is less than right, right? We want a way for these to iterate towards each other, right? Additionally, right, we said that we want to always be going from low to high, right? So to do that, we want to go from low to high. You have to figure out which one is lower between heights of left and heights of right. Heights of left is less than heights of right. Then we know that at least in our current iteration, we're going from low to high, right? Which is perfect, right? If that's the case, right, then we want to keep a reference, right, to our current height, right, which technically be 0. For the case, let's pretend it's 1 and 2 here, right? So we'd say let current equals left, right? So that's going to allow us to, or actually we'll call it start, right? This is where we started. Right? We'll say let start equals left, right, which is right here, right? We want to keep iterating forward, right, until we meet one that's greater than or equal to our original height, right? But that being the case, right, we do we want to pretty much iterate forward, right, and find a right-hand side that is greater than or equal to start. To do that, we could say while, so start is where we started, we'll say while height sub left, right, is less than, while height sub left is less than height sub start, right? So it would be here, right? Height sub left is less than height sub start, right? But if we look at where we're starting, height sub left and height sub start are going to be the same. We're going to want to increment left just a little bit, right? Just to force it to move forward, right? In the case, right, our case excludes our current case, right, which it does, right? So will 1 ever be less than 1? No, right? So we never ever run this loop. So we need a way to force it forward. So now we get, well, height sub left, right, which is now this index, which is index 2. Is the value here, which is 0, less than 1? It is. So which means we have to calculate some water, right? So we want this water variable. It's going to equal 0. We can do water plus equal, right, height sub start minus height sub left. So height sub start, which is 1, minus height sub left, which is 0. 1 minus 0 is 1, right? But the problem, like you said, we only want to add positive values. We need a way to save this. Say const p, which is for potential water, height sub start minus height sub left, right? And we'll only add it to water while p is greater than 0, right? And we'll add it to water. Otherwise we'll add nothing to it, right? Since this is a while loop, we want to go keep going as long as left is less than start, right? We would do another iteration, come back to the top and be like, is index 0, 1, 2, is index 3, right, which is an elevation of 2, less than, right, height sub left is 2, elevation of 2 less than an elevation of 1. It's not, so we want to stop, right? So we'll be here, and then this loop would also run again. I think it would be fine, right, until we get to this indice. Actually, no, because this one would start first, so we actually go this way first. So we move forward once, right? Because like we said, we have to move it forward, because 0 would not be less than 0, right? We had to move forward once, then we check between the two. Is height sub left greater, height sub left less than height sub right? 1 is not less than 1, right? So we'd actually be going the right hand side. And so with the right hand side, we actually want to just do the same, but modify some things slightly just because they're going in a slightly different direction. So start is going to equal right, but the progress step is going to be the opposite. Because left is incrementing towards the center of the array, right is incrementing towards the right hand of the array. We'll say, well, height sub right, right? So height sub right, which should start at this index here, which is 0. Which is let's just say 9, which is elevation of 1, less than, we already documented it right once, right? So actually it would be if 2 is 2 less than 1. It's not, but we moved right forward at least a little bit, right? Let's just say we're working with this iteration, right? We start at 2, and we start at this index right here. Start would be this index. Let's just call it 9, right? We'd move it down 1. We'd say, hey, well, right, which is elevation of 1 less than 2. It is, so calculate the water for that. We get 1, right? Then we'd increment, right? So we don't want to increment left, right? But right is equal 1. And here we actually want to do heights of start, which would be 2 minus heights of right. And then down here we could return water. So this makes sense. Let's see. I think in the future I want to try a brute force version of this problem and just kind of learn the different methods of doing it. But for right now, this makes sense. So we have function, max profit, we have prices, an array of numbers, returning a number. We are given an array of prices, where prices sub I is the price of a given stock on the ith day. We want to maximize your profit by choosing a single day to buy one stock, choosing a different day in the future to sell that stock, pretty much just like buying and selling in the stock market. Return the maximum profit you can achieve from this transaction. If you cannot achieve any profit, return 0. Achieve from this transaction. If you cannot achieve any profit, return 0. So we want to pretty much maximize our profit by choosing a single day to buy one stock, choosing a different day in the future to sell that stock. So from a high level view, it sounds like we'd want to minimize how much we pay for our stock, but maximize how much we sell it for in the future. So in this prices array, maximum profit you can achieve from this transaction is if you buy on day 2, price equal 1, sell on day 5, 2, 3, 4, 5, with the price equals 6, 6 minus 1 equals 5. Now if we buy on day 2, note that buying on day 2 and selling on day 1 is not allowed. Oh, right, if we buy on day 2 and sell on day 1, it's not allowed. Does that make sense? So it looks like we could also do this by iterating forward through, since we can't do past and future purchases. In this case, no transactions are done, right? Okay, so because if you buy on 7, any other day you sell it on, you always lose money. So the max profit you can make is just buying and selling in the same day. Prices always has at least one number in it. The prices go from 0 to 10 to the 4. So that being the case, that is interesting. So I'm thinking we want to minimize price paid, right? Maximize days sold on, right? And by doing those two things, we should guarantee that we have the best profit we can do. So imagine if we were to iterate through the array and keep track of the lowest we could have possibly paid for a stock. If we do that, every time we iterate through the array on each indice, we can just check if we sell it for. So basically we're trying to keep track of our lowest buy-in. If we kept track of our lowest buy-in on every day, we can check how much we could have sold it for by checking how much profit we would have made. That way we could check. So if we do 7, right, our lowest buy-in so far as possible is 7, right? If we try to make profit on this day, let's check it, right? We'll say, okay, 7 minus 7 gives us 0. So now we go to 1. What's our lowest buy-in? Is it either 7 or 1? 1 is the lowest buy-in so far, right? So we'll do 1. Now let's try and make profit. Can we sell 1? If we sell 1 on the same day, how much profit do we make? 0, right? So we're not really making any profit yet. But as soon as we go to 5, right? Now what's our lowest buy-in? 1 or 5, right? it's 1, right? Because 1 is less than 5. Now what's the best buy like sell we can do? Right, it would be 1 minus 5, which would be 4. So the max profit we could have made so far is 4, so we'll keep that. Right, then we go to 3, our lowest buying, right, still so far has been 1. Right, we try to sell on this day, right, and the profit we can make is 2, which is not better than selling on day 3. It's day 6, our lowest buying still so far is 1, because 1 is less than 6. We sell on day 6, but yeah, we sell on day 6. But that being the case, right, we try to check how much profit we can make, and it's 5, which is the best profit we've seen so far, which is what they want, which is 6 minus 1, which is 5. Go to 4, our lowest buying is still 1, the potential profit is 3, it's not better than 5. So to do that, we can keep track of our lowest buy-in, right? And if we're going to be taking the min, right, there could be, well, let's see, prices. Well, they can't sell, I guess, stocks for negative values. But that being the case, since we're taking the minimum, I think we want our lowest buy-in to be infinity. Just because if we're taking the minimum, we never really know where to put the number. If we put 0, right, our lowest buy-in will always be 0. That's not possible. If we put 1, what if our lowest buy-in is 3? So infinity works. Then we'll keep track of our max, which will be our max profit. Then we can just iterate over the array, right? We'll do lowest buy-in, right, equals the math.min of the lowest buy-in, right, and num. At the same time, let's try and sell on that day and check it between the days we've already sold on. Max is going to equal math.max max, or today's price, and we'll actually call it price. Right, max price, the price of today, right, minus our lowest buy-in. We could have gotten the lowest buy-in. Then we'll return max. So that makes sense. I'm going to try a different version of this in the future. Maybe you try a recursive version. That makes sense. So here we have a function toSum, given an array of integers nums and an integer target. Return the indices of the two numbers such that they add up to target. Okay, so you may assume that each input would have exactly one solution, and you may not use the same element twice. You can return the answer in any order. So given an array of integers nums, we have this array of integers, and target, which equals 9, return the indices of the two numbers such that they add up to target. 0 and 1 are the two indices. They add up to 2 and 7, which is 9, which is target. So that makes sense. So nums equals 3, 2, 4. Our two indices that add up to target are 1 and 2, and you can return them in any order. Two indices that add up to 6 are 3 and 3, which is 0 and 1, but they must be different indices. Each input would have at least one solution. You may not use the same element twice. Alright, so you can return the answer in any order. You can't use the same element twice, which is why to get 2 3s have to be 2 separate 3s to get 6. So I think one thing we could do, right, is since if we sorted our array, right, could we make this easier? Because the first one is not sorted, and the second one is not sorted, the first one is sorted. So if it was sorted, how could we make sure we could get to 9? All right, let's just say we iterated from both halves at the same time. We could say if we're 2 plus 15 is definitely greater than 9. Since that's the case, if this is sorted, then the biggest thing we can do is actually decrement 15 and go to 11, right? Now we have 2 plus 11, which is closer, right? That is still too big, so we go down, right? Because next smallest number we can make. Now the next biggest number we can make is by going down from the right hand side. I have 2 and 7 equals 9. So let's try that again. If we sort this, we'd have 2, 3, and 4, right? We start at 2 at the front and 2 at the 4. We do 2 plus 4 equals 6, return. So we actually can't sort it, because if we sort it this way, then we can't actually return the indices in the correct order. We can return the numbers this way, but not the particular indices. Maybe we could do that, right? But then we have to reiterate through the array and find the original indices. But that would be n log n with 2 more iterations of n, which is basically 2n log or 3n log n, which is just n log n. So we're really bounded by the search here. That being the case, another way, what if we used a map? If we used a map and we loaded all the numbers into the map, except the mapping to their indice in the array, right? Or in the indice in the original array, right? We could iterate through the array again and look up. If we iterate through the array, we could do 9 minus 2, right? And check if it's in the map. If it is, which it would be, right? From there, we could return the index that it is at in the original array. Now this would actually give us linear time, but linear space as well. So let's do the map version. Load nums into map based on number to the actual index in the map. Then we could iterate over nums, right? We could do target, I guess the number that we're looking for, right? Let's say the number that we have is 2, and we're looking for is 7 basically. Target would be the absolute value of the difference, so the abs of target minus num. If target in map, right, return the indexes, right? Return IDXs, and so we're guaranteed to have exactly one solution. So let's try it with this one. We could iterate over 3 and say, hey, it's 3 target, which is 6 minus 3 in the map. Yes, that is, but that it actually makes it a little bit difficult. We could just have another case, right, where we ignore our current case, right? We'll say, okay, if abs minus target in map, right, 3 would be in the map, right? But we have to also say, that's why it's important to think about edge cases. We could say, and the number, right, does not. So basically we have 6 minus 3, which is 3. We check if 3 is in the map. It is, right? But the index that it returned, the index IDX, the IDX for num, right, which would be 0, does not equal IDX, basically complement IDX. So if the IDX for the number, right, that we're currently at, which would be 0, and we get the complement index, right? No, it's not that. Okay, so we're iterating at, say it's 6 minus 3 is in the array. Basically the two numbers add up. Yeah, so if we're at the number 3, we'd say, hey, is 6 minus 3 in the array? No. Well, we'll say, now we're at 2. Well, is 6 minus 2 in the array? Yeah, 6 minus 2 is in the array. It's 4. Right? Facts. But we just want to make sure that, yeah, if the index that we get isn't the same as where we currently are. So we say, hey, is 6 minus 3 in the array? Yeah, what index? Is it the same index that we're on? Well, then we can't do that, right? That would be an edge case. So we'd have const map equals new map of number to number, right? We want to load it into the map. So for const number of nums, I would say value equals if the map has. We actually want the indices as well. So idx entries, right? I'm going to say, hey, does the map have this number, right? And this also is only works if they're only unique elements. Return indices of the two numbers as they add up to target, and we assume that each input would have exactly one solution. So if the input only has one solution, okay, only one valid answer exists, and there can't be more than one number. Basically, because we want to avoid having to map two values to a number. So if we have two ones, right, we wouldn't know which one to choose. But if there's only one value, no, you can have 1, 1, 1, 1, 1, 1, and our target is 6, and these two numbers add up to our 3 and 3. If that's the case, there's only one answer that exists, then we should be able to return the correct indices. So it actually doesn't matter how many duplicates there are. So if the map has a number, we'll get the. Oh, we actually aren't. We actually aren't doing numbers to occurrences. We're doing numbers to index. So we can just do map.set number to idx. Right now we want to iterate over number, right? But we still want the idx and the number. And so we want to calculate the complement, right? The complement would be the target math.absolute value of the target minus num, right? So that would be 2 minus 9 gives us 7, right? And now we basically want to check, right, the complement index, right? We'd say math.get index of the complement, right? We'd say if complement idx equals num, right? We're just going to continue because it's not something we can tolerate, basically, right? So in this case, the index we'd get would be 0, right? We'd say, hey, get the complement, which would be 6 minus 3 in the map. Well, that would get us 0, right? That gets us 0, then basically, that gets us 0, then if that gets us 0, then we want to continue, right? Because we can't do that. We have to have at least 2 indices to return. They can't be the same because we can't use the same element twice. We get to 3, right? We look it up in the map, and since map has insert order, we'll be able to return 0. 1, which would not be the same, right? So we basically check if it's in the map, right? And we only want to do this, right, if basically if complement, so if complement idx equals num, right? So let's just say now we're at 7, right? We do 9 minus 7, which gives us 2. and we have the confidence index, which is 0, right? I think it means that we're good, but when we have 15, we do 15 minus 9, which gives us 6, right? Or we have to check if it equals the target, basically. But if the complement exists, then it does exist. Huh? So this version of it, so we want to do if it's in the map. Oh, we just calculated the complement here. So you still want to check if it's in the map, right? So if map.has, right, and that's what complement IDX is checking, but it could return 0, so it's a little bit difficult. If the map has the complement, right, then here we're actually now safe. We can actually return that indice, the tuple of indices, and we want to return IDX, right? Complement IDX, right? So 15 minus 7 gives us 6. Is 6 in the map? No. So we keep going. 7, if 9 minus 7 in the map, it is. So we return IDX, which is 1, and the complement IDX, which is 0. And since a value has to exist, we shouldn't have to worry about returning anything out of this. So I thought if complements IDX, which equals 3, oh, not if it equals the number, it's if it equals IDX. So I returned undefined. So we have IDX and num with num's entries. We start -1. I mean, we got -1, -5. We have -1, right? Calculate the complement. The complement is 8. Absolute value of 8. So 8. We're saying the actual answer is -2 is 4. 2 and 4. 0, 1, 2, -3, -5. Oh, I see the absolute target mark. Oh, that does make sense. So we're at -1, right? If the target is -8, -8 minus -1 gives us 7, and then 6, 5. I think it's actually better if we just do numbers are negative. If numbers are negative, then how would we go about this? The absolute value, maybe not the absolute value. But we need the complement. And we get the complement. Again, the target, which is -8, minus the number, which is -1. But I'm seeing why it's returning undefined. That's complement. I mean, the complement doesn't exist, right? Let's reread the problem. You can just see the two numbers, it's just they add up the target. try to get the absolute value, then it kind of changes the angle that we're coming at. Basically, if target minus num, so if we check that our issue, if we just do, this means the complement. But if we're at -1, right, what's the complement that we need? We need -7. So it's -8 plus the value. So basically, we do target minus num, and it's less than 0. Maybe the way we want to go about it is that we get the complement by doing target should be -8 plus -1. Otherwise, we do the version we're doing right now. Target minus num. Yeah, what am I doing? I'm coming at this from the wrong angle. There's that one case that messed us up. It's absolute value. If we take away the absolute value, does this work? So it's just regular. We have -8, right? -8 minus number. -1, that would be -8 plus 1, which would be -7. Negative, so that'd be -6. And then negative, we have -3, and the count would be -5, so it's just target minus num. Oh, the addition game is trash. Our addition is not good. That makes sense. I need to reread the solution. We force approach a simple loop to each element x, find if there's another value that equals to target minus x. 2pass hash. So their version, they just do target, right? How do they handle the indexes not being the same? Oh no, this is a iterate over the numbers, they create the complement. If the map contains a key for the complement, then return map that complement I. And they put map that num sub I. Oh, if we do the 2pass, then you have to check right the complement does not equal I. I see.